The project of mine is the application of optimization on two-stratum system of flash thermography and bonder jetting. Bonder jetting is additive manufacturing that uses bonder to collect powder particles to create desired pattern of one layer. Then layer after layer, the wanted part can be obtained. Then, following by post-processing, the final mechanical property and final dimension can be obtained. There are two factors that affect the final mechanical property and dimensional accuracy of the final part. They are packing density, the density of the powder, and saturation level, the amount of bonder that is deposited into the powder. They all have to keep in the reasonable domain to guarantee the best performance of the printed parts. But in order to control them, some measurement is needed to monitor these key factors. And these two key factors are known to be collected with the thermal property of the powder. So, flash thermography technique is used to measure the thermal property of the powder. It uses a thermal flash to apply a thermal impulse onto the sample, and then IR camera is used to record the surface temperature after the flash. The traditional usage of this technique is for aero industry, for solid parts. The traditional method of flash thermography uses characteristic time from polynomial fitting of the experimental data to obtain the thermal property of the sample. It assumes that all energy absorbed at the surface and the flash is instantaneous. This is problematic for powder because for powder there will always be in-depth absorption and the flash is not instantaneous. In this case, the traditional method can only be a rough estimate of the true thermal property of the powder. And there are restrictions on the samples too. It can only work for one stratum or two strata system with semi-infinite thick bottom. Stratum here means a layer, a sheet of material with the same thermal property. I use this word to distinguish from the concept of layer in bonder jetting. And also, the initial temperature distribution has to be uniform. Now, this is a great problem because if we want to monitor the BJ printing process, we really need to flash it more often. But in that case, the initial temperature distribution in the sample can create great error to the measurements. So in order to solve these problems, curve fitting method based on optimization is used. The key is to find an analytical solution that has the least square error with the experimental data. The benefit of this method is that the analytical solution can involve different parameters to express in-depth absorption, flash duration, or different initial temperature gradients. The flexibility of analytical solution combined with optimization can relax a lot of constraints in traditional method, and this project is only a start. So in order to compare with the traditional method, I created a sample that can be measured by traditional method. It is a 1.4 mm 316 L powder resting on tape. The tape is thin and its thermal effect can be detected. The powder is considered to be directly exposed to air, and the air beneath the powder is so thick that now we can consider this system as a two-strata system with semi-infinite thick bottom. The measurement of the traditional method is used to set up boundaries in the optimizer of the project, and the IR camera film about 60 seconds. Now let's look at the schematic and the simplest PDE system. So this PDE system assumes all energy is absorbed at the surface and the flash is instantaneous. No matter how we change the PDE system in the future, we all have to know the thickness of top stratum and the thermal diffusivity and thermal conductivity of the bottom stratum to obtain the thermal property of the first stratum. Therefore, there are three variables in this simplest PDE system. They are major measurements, thermal diffusivity, and thermal conductivity of the top stratum, and minor measurements. Minor measurements means that we involve this factor to better approximate the experimental data. For here, there is only energy magnitude. Now, let's relax the constraint. First, we relax the initial temperature distribution. Rather than thinking about the in-depth absorption and flash duration, we just consider this. We assume that the initial temperature distribution right after the flash is assumed to be exponential. In this case, this PDE says the initial condition is changed, and this becomes a four-variable system: major measurements and minor measurements, magnitude of initial temperature distribution, and parameter of penetration. Now, this is the analytical solution of the second PDE system. So Sn is a transformed initial temperature distribution, and n is a norm. Mu n is an eigenvalue obtained from this following equation. Now let's look at the most robust PDE system. It uses a free term to express the penetration depth and also the flash duration. Of course, now initial temperature go back to 0. Heaviside function is a step function that I use to express the flash duration. So although in the experiment, the flash duration is 400 microseconds, but in the optimizer, it is set to 400 to 500 microseconds. This is because after the lamp is shut down, the magnitude of the lamp will have a decay process, and this can still have extra energy to the sample, and this can create error. So this PDE system becomes a 5-variable PDE system: major measurements and minor measurements, flash duration, penetration coefficient, and magnitude of the flash. And this is the analytical solution of the system. As you can see, the more complex the factors are considered, the more complex the analytical solution is. And this leads to 2 modes of optimization method. The first method is to use gradient-based method. That's straightforward. We just get the gradient and find the minimum. The second one is particle swamp method. The reason why we need to use gradient-free method is this. If we only want to measure a few points on the sample, then we can use gradient-free method, a gradient-based method. But in some occasion, we need to know the distribution of a whole region. In that case, there are thousands and thousands, hundreds and thousands of pixels in this region, and this will have hundreds and thousands of experimental data sets. If we use the analytical solution of PDE2 and PDE3, for every data set, it will probably use 5 to 10 minutes to process it. That will take days to go through all these experimental data sets. So to solve this problem, we would first calculate the analytical solution for a range of thermal property and other factors and store it in the solution pool. And we will use particle swamp method to capture the analytical solution that best fits the experimental model. If we have the pool, usually it will take 1 second to find the solution. But the only problem is that it may take hours to create a solution pool. Usually 1 to 2 hours, actually. But compared with the days of gradient-based method on this scenario, still it saves a lot of time. Now let's look at the fitting results. The fitting starts from 0.5 seconds to 18 seconds. This is because, as you can see from here, when the time is greater than smaller than 0.2, actually no method can predict the initial temperature profile. This is because in the PDE system, we assume that the material is homogeneous. But actually, for powder, especially when the powder is near the surface, that's not the case. And also, after 18 seconds, the error of the measurement will be increased due to convective heat loss. So we can see the fitting here is pretty good, and the improved method is so well we cannot see the line, but the traditional method can still see it. Now let's compare the results quantitatively. As you can see, by using optimization and improved model, the least square error dropped 1 order of magnitude, and the thermal diffusivity and thermal conductivity are in the reasonable range. As for the minor measurements, the penetration coefficient agrees well with other literature that indicates the penetration depth is not deep for powder, and also the energy decay is captured. As for energy magnitude, it will be studied in the future for the energy absorption of powder. Right now, I don't have first-hand information. Now, let's talk about the improvement of this work. First and foremost importantly, more accurate measurement is obtained for powder, and we can easily apply this method to other porous media, such as printed powder and BJ printing pots. In this case, an accurate correlation between thermal properties and packing density and saturation level can be obtained for BJ printed pots. Now, if we test on different samples, of course. Now, this is the foundation to monitor BJ printing pots and the BJ printing process. Secondly, since the restriction in initial temperature distribution in depth is now relaxed, using superposition of PDE2 and PDE3, we can easily solve the and PDE system with free term and initial temperature distribution. This means that we can accurately measure the thermal property of a sample despite the presence of temperature gradient in the sample. This means that the cooling interval between every flash is greatly shortened. And monitoring BJ printing process is now possible. In this case, filled part can be filtered out before the printing process is finished. This saves time, energy, and material, and we have better control over the BJ printing process. At last, although in this sample the bottom has a semi-infinite thickness, however, we now can obtain analytical solution of any cyclist ratio between two strata system. This means the restriction in bottom cyclist is also relaxed. Also, it's really not difficult to use the same mathematical tool to solve multi-stratum PDE system. In this case, we can monitor multi-stratum system, and that is the powder bed of BJ printing process. This means the application of optimization on flash thermography not only expands the usage of flash thermography on a lot more scale, but also the successful rate of BJ printing is increased and the yield is also increased. Thank you.